Hello, in this video we are talking about similar vertices. So that is looking at the automorphisms and seeing how the vertices of the graph relate to these automorphisms. Okay, let G be a graph and we'll define a relation on its vertex set by the vertex U is related to the vertex V if there exists an automorphism such that phi of u equals v. So there's some automorphism that sends the vertex u to the vertex v. In that case, we'll say u is related to v. So we can show that R, this relation, is reflexive, symmetric, and transitive. So maybe real quickly, why is this relation reflexive? So remember, reflexive means that u is related to u for all vertices u. And that's not too hard to see because what automorphism does that? Well, it's the identity automorphism. So I'll say phi equals the identity automorphism. Shows that every vertex is related to itself. It's symmetric, so remember symmetric means that if u relates to v, then v relates to u. So what can we use here? So if u relates to v, this means that there's some phi such that phi of u equals v, and we want to show that v relates to u. Well, the inverse of this will work. So use phi inverse for this. So if phi of u equals v, then phi inverse of v is equal to u. And phi inverse is an automorphism, right? Because automorphism is a group. Finally, it's transitive. So remember, with transitive, we want to say that if u relates to v and v relates to w, then u relates to w. Sorry, I went off the screen a little bit there. Then u relates to w. So if u relates to v, that means there exists some phi 1 such that phi 1 of u equals v. If v relates to w, that means there's some phi 2 such that phi 2 of v equals w. And so what I can do is I can compose these. So that is, I can do phi 2 composed with phi 1. Composed with phi 1. And that will, we can check, so phi 2 of phi 1 of u, well, phi 1 of u is v, so this is phi 2 of v, and phi 2 of v is w. And so this automorphism, phi 2 circle phi 1, sends u to w. And so that means u relates to w, and hence it's transitive. So that tells us that this relation is an equivalence relation, and hence it partitions the vertex set into equivalence classes called orbits. Now, any two vertices that are in the same orbit, we call similar vertices. All right, well, let's illustrate this with an example because it'll be a little bit easier. So here's this graph G, and the first thing I want to do is compute the automorphism group of G. So it's not too hard to see that that this is the cyclic group of order 3, so just the rotations, right, by 120 degrees each. The rotation, so alpha 1 would send V3 to V2, V2 to V4, V4 to V3, and then V7 to V5, to V9, back to V7, V8 to V6, to V10, back to V8 would be 1, and then the square of that would be the rotation in the other direction. And those are the only, together with the identity, those are the only 3 automorphisms of this graph. So what are the orbits of G then? The orbits of G, so notice V1, there's no automorphism that sends V1 to any other vertex of the graph. It's fixed by all automorphisms. And so that means that V1 is in an orbit by itself. However, V2, V3, and V4, these are all similar vertices because given any pair of them, V2 or V3, I can find an automorphism that sends one to the other. Right? If I want to send V3 to V2, I do a rotation in that direction. If I want to send V3 to V4, I do a rotation in that direction. If I want to do V2 to V4, I would do a rotation in the clockwise direction. I could use, that would be right? V4 to V2, that would be alpha 2. So for any, so these are all in the same orbit because given any pair of them, there is some automorphism that sends one to the other. Similar for V5, V9, and V7. Those are all similar vertices. And V8, V6, and V10 are also all similar vertices. So these are the orbits of the graph. Now, why might we care about the orbits of these graphs? Well, it's really highlighting the symmetry of the graph, this idea of two vertices essentially being the same up to automorphism is the idea of orbits. So in particular, it makes computing properties of the graph or properties of vertices a lot easier. So for example, computing the eccentricities of the vertices of this graph can be made easier by noticing the orbits. So in particular, if you are a programmer, want to do programming on graphs, some sort of coding on graphs to, say, compute properties of the graph, it might be helpful to first find the orbits. And this is how we can make it easier. So I can compute the eccentricity of, say, V1 and just compute the distance from V1 to vertex farthest from V1. It is 2. And then I can compute, let's say, eccentricity of, I don't know, V2. So from V2 to any other vertex, 1, 2, 1, 2. It's also 2. And what's cool is since the V2 is similar to V3 and similar to V4, right? Since we know there's an automorphism since V2 to either of those, that means they all actually have the same eccentricity. That we don't have to do any more computation there except with just one vertex. So it's going to reduce the problem of finding the eccentricity of every vertex from 10 vertices down to just 1, 2, 3, 4, one for each of the orbits. And again, we can keep going like this. So eccentricity of, let's say, V5. 1, 2, 2, 2. Let's see, how do we get to V7? 1, 2, 3. 1, 2, 3. I think 3. And that should be the same then for V7 and V9. Those eccentricities are all 3. And then the same should be true for V6, V10, and V8. Let me do a quick check. Yeah, it takes 3 to get to V9 from V6. So eccentricity of V6 is the same as eccentricity of V8, the same as eccentricity of V10, and that's equal to 3 as well. So if two vertices are in the same orbit, then their eccentricities are the same. And really any structural property of the graph, we can aid the computation by noticing the orbits of the graph. So the other thing that would be the same among vertices, among similar vertices, would be, say, the degree of any two vertices. So let me say that here. If U and V are similar, then degree of U is equal to degree of V, right? Because automorphisms have to preserve degree. And so we can also say that. So that's a nice thing to note. Of course, the converse of this is not true. Just because two vertices have the same degree does not mean they're related. Same thing for eccentricity. Right here we see V5 and V6, for example, each have eccentricity 3, but they are not similar vertices, just like the degree. Okay, I think that's all I want to say here about orbits of vertices.